Hello learners, welcome back to my channel Shraddha's Physics. In this part we will discuss on the Langevin's theory of paramagnetism. In the previous lecture we have already discussed about the dimagnetic material, paramagnetic material and the ferromagnetic material. In case of the dimagnetic material, we know when you place a dimagnetic material in the presence of an external magnetic field, then it will be magnetized in the opposite direction to that of the field. But in case of the paramagnetic material, when you place a paramagnetic material in the presence of an external magnetic field, then it will be weakly magnetized in the direction of the field. But in case of the ferromagnetic material, if you place a ferromagnetic substance in the presence of an external magnetic field, then it will be strongly magnetized in the direction of the applied field. So this is the basic difference between dia, para and ferromagnetic material. Now let us see what is paramagnetic substance briefly. That is, in case of the paramagnetic substance, we know when it is placed in a magnetic field, then they will be weakly magnetized in the direction of the applied field. And the example of the paramagnetic substances are aluminum, antimony, copper sulfate, crown glass, etc. Since the weak induced magnetic field it is in the direction of the applied field, the resultant magnetic field in the paramagnetic substance it is slightly more than that of the external field. So the magnetic susceptibility of a paramagnetic substance it is positive and having a small value. So we can represent the relative permeability, that is mu var equal to 1 plus the susceptibility chi, and here this permeability it will be slightly greater than 1. So we can say that this paramagnetic property it is a weak form of the magnetism. This paramagnetism is due to the presence of the unpaired electrons present in the material. So all the atoms with the incompletely filled atomic orbitals they are paramagnetic, and due to their spin unpaired electrons have a magnetic dipole moment and it acts like a tiny magnets. An external magnetic field it causes the electron spins to align parallel to the field, causing a net attraction. That is, if you place a paramagnetic material in the presence of a external magnetic field, that is suppose B, then what will happen? Then it will try to move this electron, that is it will cause the electron spin to align parallel to that of the field. That is, if you place a bar magnet, it is suppose in this direction, this is suppose north pole and south pole. So a torque will be applied here so that it will try to align this magnet in the direction of the field. And like the ferromagnet, paramagnets do not retain any magnetization in the absence of the externally applied magnetic field. That is, if you remove that external magnetic field from that paramagnetic material, then you can see the magnet will be very weakly magnetized. Because the thermal motion it will randomizes the spin orientation of the paramagnetic substance. So the total magnetization drops to 0 when the applied field is removed. Even in the presence of the field there is only a small induced magnetization because only a small fraction of the spin will be oriented by the field. So this fraction it is proportional to the field strength, and this explains the linear dependency. From the classical point of view, the alignment can be understood to occur due to the torque being provided on the magnetic moments by an applied field which try to align the dipoles parallel to the applied field. Just I have told you. That is, this part we are going to discuss briefly. That is, in case of the Langevin paramagnetic theory, we will discuss this part. When you apply some external field to a bar magnet, then because of this torque it will try to align this bar magnetic material in the direction of the external applied magnetic field. External magnetic field or the applied magnetic field. So the true origins of the alignment it can be understood through the quantum mechanical properties of the spin and angular momentum. This basically can be understood by the quantum mechanical behavior, that is the properties of the spin and angular momentum. But here in this part we will see the classical behavior of the paramagnetic material. If there is sufficient energy exchange between the neighboring dipoles, then they will interact and may spontaneously align or anti-align and form magnetic domains resulting in ferromagnetism. That is, if they will align, then it will form the ferromagnetic metal. If they will anti-align with that of the external field, then they will form the anti-ferromagnetic material. But the paramagnetic behavior, it can also be observed in the ferromagnetic material that are above the Curie temperature. That is, this is the important one. The paramagnetic behavior, it is observed in the ferromagnetic material when it is just above the Curie temperature. But in case of the antiferromagnetic material, when it is above the Néel temperature, it will show the paramagnetic behavior. In case of the ferromagnetic material, when it is above the Curie temperature, then it will show the paramagnetic behavior. But in case of the antiferromagnet, when it is above the Néel temperature, then it will show the paramagnetic behavior. Now let us see the causes of the paramagnetism. In a paramagnetic substance, the individual atoms, it has the small net magnetic moment. That is, the electron spins on orbital motion having net circulating current that is not zero. That is, in this case you can see when there will be no magnetic field is applied here. In this case we will discuss, and here is the case when the field is applied to the paramagnetic matter. So the atoms or molecules or ion as a whole has a net magnetic moment, that is, each act as a magnetic dipole. Suppose if I will consider in the absence of the external field, the dipoles of the paramagnetic substance, they are randomly oriented. That is, in this case you can see each individual, they will be randomly oriented in the different direction. Randomly oriented means they will be, the direction will be different, and therefore the net magnetic moment of the substance, it goes to zero. That is, this substance, it does not exhibit any paramagnetic behavior. But in the presence of the external magnetic field, the dipoles are partially aligned in the direction of the field. So we can see that in this case, when you apply some magnetic field in this case, so this dipole, now it will try to align themselves in the direction of the field. So here in the first case you can see it is randomly oriented, but now on the application of the field, if the field is in this direction, now it will try to align themselves in the direction of the field. Okay, and this magnetic field, it will retain in that magnetic material up to the magnetic field applied in that of the paramagnetic material. But when you remove that applied field, when you remove this external field, external magnetic field from that paramagnetic material, then it will lose its magnetic property. This is the basic reason of the paramagnetic material, or the basic properties of the paramagnetic material. According to the laws of atomic structure, the electrons in an atom, they have a tendency to exist in pair. So if there are two electrons, they will be always exist in pair with their angular momentum vectors pointing in the opposite direction. That is, if this electron is in this direction, then the other one, it will be directed in the downward direction. So for most of the atoms which have an even number of electrons, the total angular momentum is zero. When there will be an even number of atoms, that is, if suppose there are 2 electrons, then in that case this 2 is a even number, 2 or 4 or 6, these are your even number. So in this case the total angular momentum is zero, because you can see one having upward direction and other having downward direction, they will get cancelled. So having the even number angular momentum, then there will be even number of electrons, then there will be total angular momentum, there will be zero. And such atoms of the electrons, the total angular momentum zero, they will have the net magnetic moment, dipole moment, that will be zero, and they will form the dimagnetic material. And atoms with the unpaired electrons, that is an odd number of electrons, at least one electron which is unpaired, such atoms tend to have a net magnetic moment, and they will form the paramagnetic material. In a molecule consisting of two such atoms, that is the two electrons which are originally unpaired in the atom, will pair off with their angular momentum pointing in the opposite directions. So the molecule thus has a zero magnetic moment, and now it will behave as a dimagnetic particle. But oxygen is the exceptional case. Now let us start with the Langevin's classical theory of paramagnetism. Langevin considered a paramagnetic gas containing n atoms per unit volume. This n atoms per unit volume, each having a permanent magnetic moment, suppose mu. The mutual interaction between the magnetic dipole, it was assumed to be negligible. That is, there will be no attraction between the magnetic dipole. But in the presence of the magnetic induction, that is the magnetic field, these dipole tend to orient themselves in the direction of the field in order to minimize their energy. So the thermal energy at the ordinary temperature, it resists such an alignment of the dipole. That is, it will try to oppose this alignment of the dipole, and in the thermal equilibrium, the dipoles orient themselves at an angle theta with the direction of the applied field. Here you can see if there are some external magnetic field is given to a magnet. This is suppose the magnet. Now you can see here, this is suppose the bar magnetic is placed in the presence of the external magnetic field, that is suppose B. So now because of the torque, it will try to align in the direction of the magnetic field. So now suppose, let me draw, this is your dipole length, this is your one is north pole, another having the south pole. So this is suppose, this angle is suppose theta. Okay, this angle is suppose theta. So in the thermal equilibrium, the dipole orient themselves at an angle theta with the direction of the applied field. Now the torque experienced, how much will be the torque? Now we can see in this direction, if pole strength is M, this is suppose north pole and this one is suppose south pole. This perpendicular distance is suppose its name is A. Now we can write the torque will be, torque experienced will be equal to MB, magnetic field B, M is the pole strength, into this perpendicular distance, that is NA. Now we can calculate from this, I can calculate sin theta equal to, sin theta is your P by H, P is your NA and H is your NS. So I can write this NS is nothing but the dipole length, that is your this NS equal to this much is your suppose 2L, the dipole length is suppose 2L. So I can write NA will be equal to, so there in place NA will be equal to 2L sin theta. 2L sin theta. Now if I substitute the value, this will be equal to M into B into 2L sin theta. 2L sin theta, this is the torque experienced. Now you can see. Now the torque experienced will be equal to, here from this expression, this M into 2L, this is nothing but your magnetic moment mu. Mu, you know, mu equal to pole strength into the distance 2L, dipole length. So this M into 2L, that is your mu into B sin theta. This is your torque experienced. So this is your torque experienced. So if an external force displaces it through an angle d theta, then the work done by the force will be tau into d theta. This will be tau into d theta. Tau d theta, that will be simply equal to mu b sin theta into d theta. The external force will be torque into the displacement, that is the angular displacement, that is d theta. So this will be tau into d theta, that will be mu b sin theta into d theta. So basically you can see here, this angle is suppose d theta. Okay. So the total work done in displacing the atomic dipole to the position making an angle theta with the direction of B will be equal to, if we will integrate this mu b sin theta d theta from 0 to theta, then this will be mu b into the derivative of sin theta d theta, the integration of sin theta d theta will be minus cosine theta, and substituting the upper limit and lower limit. So simply just like write like this is your simply integration over mu b sin theta d theta. So that will be equal to minus mu b into cos theta. Now from this expression, the work is stored in the atomic dipole as it's the potential energy. So now we can calculate the potential energy of the dipole will be equal to this minus mu b cos theta. The potential energy will be nothing but minus mu b cos theta. So using the Maxwell-Boltzmann distribution law from the statistical mechanics, the number of magnetic dipoles having this particular orientation, it will be proportional to your exponential minus E by kt. E is the potential energy or the internal energy, you can say. So in place of energy you can substitute, this will be minus mu b cos theta. So this minus with this minus, that will become plus, this is a positive, mu b cos theta divided by kt. This will be exponential mu b cos theta divided by kt. According to the statistical mechanism, the probability for a magnetic dipole to make an angle between this theta and theta plus d theta with the magnetic field or the number of dipoles dn having axis within the solid angle d omega lying between the two hollow cones, we can write this dn, it will be proportional to your potential energy, that is exponential mu b cos theta divided by kt into the solid angle d omega, and that will be equal to, if I will remove this proportionality symbol, I will write the proportionality constant, suppose c, exponential mu b cos theta divided by kt, and in place of d omega we will substitute the value of the solid angle, that will be 2 pi sin theta into d theta. So now the total number of atomic magnet in unit volume of the paramagnetic material, now we can integrate, n will be equal to the integration over dn, that is from 0 to pi, that is equal to 2 pi into integration over 0 to pi, this will be c, exponential this mu b by kt, if I will consider that to be alpha, then this will be alpha cos theta into, here you can see this 2 pi is here written here, this will be simply sin theta d theta. Okay, mu b by kt here I have considered, this is your alpha. Now if I will consider the cos theta to be x, then this will be minus, taking the derivative of both sides, I will get minus sin theta d theta, that will be equal to dx. And now if I write, the n value will be equal to 2 pi c into, in place of exponential alpha cos theta value will be x, so this will be exponential alpha x, and in place of sin theta d theta I have to substitute minus dx, so simply this will be minus c 2 pi exponential alpha x dx. And again here you can see, when you put the value of theta that to be 0, cos 0 is your 1, so x value will be plus 1, and when you put the value cos theta to be pi, then cos pi is minus 1, so this value is your minus 1. Okay, so now integrating this we will get, this will be c into 2 pi, these are your constant, minus c 2 pi is your constant. The integration of exponential alpha is dx will be exponential alpha is divided by alpha over the integration plus 1 to minus 1. If you remove this minus sign and if you change this limit, this is from plus 1 and this is your minus 1 to plus 1, then this will be simply c2 pi divided by alpha into exponential, the upper limit I will put exponential alpha minus exponential minus alpha, or from this relation we can write c will be equal to n into alpha, n equal to this much, so this will be n into alpha divided by 2 alpha exponential alpha minus exponential of minus alpha. So the magnetic moment contributed by each atomic dipole in the direction of the field B will be equal to mu cos theta. The total magnetic moment therefore contributed by the atomic dipole will be equal to C into integration over 0 to pi mu cos theta exponential alpha cos theta into 2 pi sin theta d theta, this expression. But here this exponential alpha cos theta equal to, in place of alpha, here this is mu b divided by kt. In place of mu b by kt, in place of mu b by kt, we have substituted the alpha value. So simply by substituting the alpha value, this will be exponential mu b cos theta divided by kt. And this exponential x term, we can represent this by summation over x power n divided by n factor, or this is simply 1 plus x power 1 divided by 1 factorial plus x square divided by 2 factorial and so on. So simply for this will be 1 plus this total value is your x, that is 1 plus mu b cos theta divided by kt, and neglecting all other higher order terms, I can represent like this. So the average magnetic moment per atom in the direction of the field, we can write average mu will be equal to C into integration 0 to pi mu cos theta dn divided by integration over 0 to pi dn, that is the total number of atoms, that will be n integration over dn. In place of dn, if I will substitute this value, this will be C into 2 pi 1 plus mu b cos theta divided by kt sin theta d theta, and here we have substituted again the dn value. Now if I will calculate this, you can see here the integration over 0 to pi cos theta sin theta d theta, that is equal to 0. but the integration over 0 to pi cos square theta sin theta d theta, that is equal to, if you calculate, this value is equal to 2 by 3, and the integration over sin theta d theta, its value is 2. And simply if I substitute this value here, we will get the average value of mu will be equal to 2/3 mu square b by kt divided by 2, or that is simply equal to mu square b divided by 3 kt. I think you can solve this expression. So the magnetic moment average will be equal to, or the magnetic dipole moment per unit volume, or the intensity of magnetization, this can be calculated as equal to m, or this is your intensity of magnetization I, that is equal to n. Simply I will multiply in this expression. This will be n mu square b divided by 3 kt. Okay, and that is nothing but equal to, I can write this total term is your constant, and that is your susceptibility, or the paramagnetic susceptibility, that is your chi of p. So m equal to chi p into b, or this chi p can be written as m divided by h. So in place of, this is your actually, yes, m by h. So this will be mu naught n mu square divided by 3 kt. So from this expression you can see this susceptibility is inversely proportional to the absolute temperature T, and this mu naught mu square divided by 3k, this is called the Curie's constant. And this Curie's law, it holds good when this mu b is very less than kt. That is the susceptibility of a paramagnetic substance, it varies inversely as the absolute temperature. Susceptibility of the paramagnetic substance, it varies inversely as the absolute temperature. So this is all about your Langevin's theory of paramagnetism. That's all for today. Thank you.